going to tell us about fusion rules of W-Algebras and rationality of W-Algebras.
Okay. First I'd like to thank the organizer very much for the invitation to speak here. So the title of my talk is Rationality and Fusion Rules of Affine W-Algebras. I'm going to be reporting on joint work with Tomiyuki Arakawa. So basically, affine W-algebras, certain interesting class of vertex algebras. So it's a talk about vertex algebras, or in physics language, more or less the same thing as a conformal field theory. Which are defined starting from certain simpler class of vertex algebras called the affine vertex algebras, or WZW models, by a process called either quantum Drinfeld-Sokolov reduction or Hamiltonian reduction, which is a certain kind of cohomology. So when I say that they're interesting vertex algebras, what I'm going to mean is that in certain cases, they turn out to be rational vertex algebras. And being a rational vertex algebra means more or less that its representation category is semi-simple, finite number of irreducible objects and complete reducibility of all modules. And furthermore, in this setting, one gets various other structures on this representation category. So for example, it's going to be a tensor category, even something more exotic called a modular tensor category. And so the so-called fusion rules of a vertex algebra or a CFT are basically the tensor categorical structure. I should say the level of the Grothendieck group. So in the first half of the talk, I want to briefly indicate how we prove rationality for certain examples of W-algebras. In the second half, pass to calculation of fusion rules in these cases. Okay, so everything begins with finite dimensional simple Lie algebra. G, with all the trappings, so triangular decomposition. Then we have a root system, delta, set of simple roots, alpha 1 through to alpha L, so it'll be rank L, Verma modules, and their irreducible quotients, L of lambda, here where lambda is any weight. And starting from G, we have associated affine Lie algebra, which is basically So the Kac-Moody algebra that you get by starting with the Dynkin diagram of the finite guy and then adding a node to the Dynkin diagram in a particular location. So for example, at D4, you would then add a node here, and I'll index that by 0. And also, just purely for notational purposes, I'll want to introduce the fundamental weights. Which is dual to the set of simple roots. Oh yeah, and then I can define the Weil vector. Okay, so an important definition to get started is the notion of an admissible weight, or what I'll actually define as a so-called principal admissible weight. So the definition is as follows. So I'm going to define the so-called root subsystem associated with an arbitrary weight lambda to be the following thing. So I take all of those roots in, this is the affine root system, which satisfy the following property, that lambda plus rho paired with alpha, well, the co-root, is an integer. So this is a general definition, and the definition of the weight lambda being admissible is that this root subsystem is actually isomorphic to the original root system. Okay, so this imposes a condition on lambda. Okay, and then we'll denote PRK to be the set of, well, principal admissible weights lambda of level k. And in fact, for this set to be non-empty, this number k has to be a rational number, it turns out. One more piece of notation. I'm going to write twiddle for two weights to mean that, well, that lambda and mu are related by this standard dot action of some element in the finite Weil group. Okay, so that's some necessary notation. Now going back to an arbitrary level k, though I'll soon specialize to the case of k, an admissible level. So if we take this zeroth fundamental weight and take any multiple of it k, then the irreducible module at that level turns out to have this algebraic structure known as vertex algebra. Okay. So I won't state the full definition of vertex algebra, but it's an interesting algebraic structure which plays an important role in the representation theory of affine Lie algebras and also has connections with physics and so forth. And the important point here is that there's also a notion of module over a vertex algebra, and in the present case we have the collection of all modules over this vertex algebra is just some subset or subcategory of the modules of the original affine algebra. Okay, so we think of this being a module over this vertex algebra as being a condition that singles out some interesting subcategory of G hat modules. Okay, that was it. There we are. Okay, so let M be one of these L K lambda modules. And let me also assume that it's graded, or positively graded. Maybe by finite dimensional graded pieces. I won't be too fussy about the conditions. So now, since this thing is graded, I want to consider the lowest graded piece. Because a module over the vertex algebra is a module over G hat, and the universal enveloping algebra of the finite algebra is going to act then on each graded piece because it'll preserve the degree. So I'll get a module over U of G. But then depending on the level that I chose, K, you know, this it could be that there's some relations. So it won't be an arbitrary module of U of G that can occur here, but there'll be some ideal. So every one of these modules that come from a representation of the vertex algebra will in fact be a module over this algebra divided by some ideal. This ideal is going to depend on the level K. So in fact this is a general procedure which can be done for all vertex algebras. But I want to explain how it works in general, which in the general case is known as the Juju functor. So it's a general fact that for any vertex algebra, there's some associative algebra called the Juju algebra, such that, well, firstly, if you do this procedure, if you take any positively graded module of the vertex algebra and look at the lowest graded piece, it becomes a module for the Juju algebra. And there's a remarkable theorem, Juju, so here V is an arbitrary vertex algebra, and then we have this functor to modules over at Juju algebra. And always, in complete generality, this functor is a bijection on irreducible objects. So it doesn't capture everything in the representation theory of V, but it captures really a lot. So the point here is that we're wanting to study the representation theory of this vertex algebra by reducing things to a sort of finite dimensional case. Okay. Well, it's yeah. I'm not saying it explicitly. It's some ideal. Well, let's see. So, if k were generic, say an irrational number, then it would be nothing. It would be 0, because the irreducible quotient would be the same as basically as the Verma module. The idea is basically when k assumes some specific values, certain rational values, then this irreducible quotient becomes smaller than the Verma module. So being a module over this vertex algebra becomes a non-trivial condition. Yeah, which sort of goes into this ideal somehow. More precisely, I could say that this is the Juju reduction functor applied to the ideal, such that so this irreducible module is the Verma module divided by some ideal. You apply the Juju functor to that ideal, and that's what IK is.
So the same like in the Juju theorem.
Yeah. Okay, so our first main theorem, but one which I won't really state in any detail, says about the structure of this algebra. So in fact, this is actually given by a direct sum over a collection of simple algebras, each of which is U of G divided by this J of lambda. J of lambda is the annihilating ideal. Sorry, let me write down the definition. Okay. Sorry? Oh, I'm sorry. Yeah. Well, yeah. What does it mean for the number k to be admissible? It simply means that the weight k lambda 0 is admissible. Okay, it makes sense to have this sum going only over this quotient of the set of principal weights divided by the Weyl group action, because it's well known that this ideal J lambda depends only on the equivalence class of lambda modulo the Weyl group action. Okay, so the nicest possible situation is when this number k is a positive integer, because then the original affine vertex algebra is rational. In all other cases, the affine guy is not rational, but somehow this process of Hamiltonian reduction that I mentioned briefly already sort of improves the situation and tends to make the vertex algebra nicer, and in certain cases is expected to make it rational. So I won't define the Hamiltonian reduction, but the basic data that goes into it is the following. So what one has to do is first fix a nilpotent element, and then one defines Hamiltonian reduction with respect to F. So we can apply this reduction functor here. So this is the affine W-algebra of the title. And this corresponds at the level of sort of associative algebras, universal enveloping algebras, to a similar reduction functor, which is also defined in terms of the nilpotent element. And this yields what's called finite W-algebra. So this will be a vertex algebra. So we'll again have the Juju functor. And we sort of have a commutative diagram here. So the Juju algebra of this W-algebra, this affine W-algebra, is going to be certain finite W-algebra. Like that. And so since we always have this bijection between Juju algebra modules and V modules, if we can understand the structure of this algebra, this finite W algebra, then, well, at least we can find all the irreducible modules of the vertex algebra and then hope to start trying to understand the category of representations. So a piece of notation I'll just introduce before going on. So we fix this nilpotent element F. Okay, so there's this notion of a grading which is compatible with a nilpotent element that'll be useful to use. So it's simply a Z grading on the Lie algebra, which has to have this property that F lies in the -2 piece. And so then the adjoint action with F is going to lower degree by 2. And there's some further conditions which I won't mention. Importantly, we want to assume that there are no odd degree pieces here, which is a condition which is not satisfied for all nilpotent elements, but it's satisfied for many. And it can be removed, even this assumption, but it just makes things a bit simpler. So let me just briefly talk about the associated ideal. So let I be any two-sided ideal inside U of G. So as we know, U of G is naturally filtered. And the associated graded algebra of U of G is the symmetric algebra of G, which is just equal to the ring of functions on the joule, vector space joule of G, which is kind of basically the same thing as functions on G. So if we have some ideal I, then we get this associated graded ideal, which now lives inside S of G. So now we have an ideal inside a commutative algebra, so this corresponds to some subvariety of the affine space G. So I'll call that variety of I, some subvariety in G. This is called the associated variety of I. Okay, so I mentioned this because I want to quote a theorem of my collaborator, Tomiyuki. So at the same time, let me introduce a piece of notation which will be enforced throughout the rest of the lecture. So I'm going to take an arbitrary admissible level k and write it in this form. So it's a rational number. I'm going to write it as minus h plus p over q in lowest terms. H here is the Coxeter number of G. Oh, I'm going to assume AD. Yeah, all right, joule. But I'm also going to assume, for convenience, k is admissible. Yeah, but I haven't yet reached the point at which I have to assume AD type. Okay, so the statement is that the associated variety of this ideal IK Okay, so I mean, so the statement is that the associated variety of this ideal IK is the closure of O sub q. O sub q here is a certain nilpotent orbit, and it depends only on this denominator q. What is a nilpotent orbit? It's well, it's the orbit under the adjoint action of G, the group G, of some nilpotent element inside G. Okay. And two, Tomoyuki said a lot more. I mean, it's possible to identify which nilpotent orbit it is for each Q, so it's not just an abstract statement. Okay, so next I want to... okay, so what are we doing? We're trying to study, we want to understand this algebra here so that we can say something about irreducible representations of this vertex algebra. So for this, let me state a theorem of Losev about finite W-algebras. So Losev says that the Hamiltonian reduction relative to f of this algebra here is simply some direct sum of matrix algebras if we have this condition relating the weight lambda and this nilpotent element f. He also says that it equals 0 if this closure GF is not a subvariety of the associated variety of J lambda. So basically there are two cases in which we essentially can say very concretely what this algebra is. The only remaining case is when this closure is properly contained in this associated variety. So in order to say anything concretely, let me try and exclude that case. And I need to exclude this case. No, hang on. Ensure that this holds for no weight lambda among all the lambdas which appear in the sum that's going to appear in the Juju algebra. Okay. So in order to ensure this condition, let me now impose, well, two further conditions.
So the Juju algebra is filtered. The associated gradient of this guy gets a surjection from the C2 algebra that you described the associated variety as this nilpotent orbit.
Uh-huh.
So you have an embedding of the associated variety to that associated gradient to the Juju algebra into this guy. And somehow, so now you're described, so I thought that you were going, this theorem describes what this image is of this embedding.
I didn't really understand.
Yeah, so I guess I'll ask you later.
All right.
It somehow seems to me that that supposition trivializes the theorem. But
Well, no, that supposition turns this into a direct sum of matrix algebras. Oops. Okay, so we want to assume two conditions. One is that F lies in this distinguished nilpotent orbit. And another condition is slightly more technical, so I won't say very much about it, but we want to assume that every one of these twiddle orbits in the set of principal admissible weights meets this set of sort of integrable weights, where, what does this mean? Integrable with respect to this G0. Remember, G0 is the zero component of this grading of the Lie algebra. And some of that's slightly more technical. It's important to have this integrability condition to sort of understand well the reduction functor H0f. But anyway, in particular, when we have these conditions, then we have this condition over here. So we know that the Juju algebra is a direct sum of matrix algebras. So in particular, we have good control of the set of irreducible modules for the vertex algebra. And with a little bit more work, one can then show that there are no non-trivial extensions between these modules, and so one gets the rationality of the affine W algebra in this case. So part A. So, and then the statement is that all of the irreducible modules are given as Hamiltonian reductions of irreducible modules for the affine Lie algebra. Now, the lambdas have to be in this PRK, simply because of the structure of the Juju algebra. By assumption, we can take them inside this P0 plus, this integrable part. And because of this theorem of Losev, it's sort of they're annihilated if they don't satisfy this other condition regarding the associated variety. So it's only those weights lambda such that the variety of J lambda is equal to the closure of O, and is this set modulo this relation twiddle. So it's a bit of a complicated definition, but in specific cases you can really work out this set of weights. And part B is then more or less consequently this algebra, which I'll write as WK GF is a rational vertex algebra.
Sorry, in the SLM case, which nilpotent satisfied your conditions?
I can't remember exactly. If you given Q, it Tomiyuki could say that. Given Q, it determines a particular nilpotent element such that the reduction will be rational. And it's not all nilpotent elements, but it's many of them.
So, do we have the complete description of such nilpotent for SLM?
Yes, there's that case, but also the other case which I want to talk more about, and which I'll spend the rest of the lecture speaking about, for type A, D, or E, and if the subregular nilpotent. And this is uniquely defined by the condition that the dimension of this GF is equal to dim G minus the rank of G minus 2. Okay? Or so I want to talk about the fusion rules, and I'll just restrict myself to this case, subregular, nilpotent. So just to briefly recall sort of how it works. So if so I mentioned that I'm sorry. So if I take a positive integer, let's say greater than or equal to the Coxeter number, then this vertex algebra here is already rational. There's a finite number of irreducible modules, and these are given by the irreducible highest weight modules of G hat, where lambda here runs over the set of regular weights of level k. So let me just say what that is. So it's the condition that lambda, when you act on any of the fundamental co-weights, here is a positive integer. I've written this in a slightly overcomplicated way because I want to, simply for notational reasons. The usual story is that if we write down graded dimensions of these modules, called the characters, then these are modular functions. And since they're modular, then if I take the S transformation of one of them, then I get some linear combination of the others. And there's a well-known formula for the coefficients of this modular S matrix, given as a sum over the Weil group of certain exponentials here. Okay, and it's well known that one can compute the tensor product structure in the category by this explicit formula called the Verlinde formula, starting from the S matrix. So in order to write down the S matrix for these subregular W-algebras, let me introduce this matrix here. Sigma is now a sum on W. Where it's basically the same thing, except that now I insert this funny rational function here, which involves this roots. This is the only two root spaces which go into this G0, apart from the Cartan subalgebra. And this vector x here, say x, is some element in H. And the interesting thing is this formula appears to depend on x, but it turns out not to in the end. So, although I'm not sure how to write down an expression for this S matrix that doesn't depend on x, one can prove that the final result doesn't depend. Okay, and so here lambda and mu run over the following set. Okay, and the set that parameterizes lambda and mu here is this, what I'm going to call P plus subregular, which are sort of dominant integral weights that are kind of degenerate along exactly one root hyperplane. Okay, so finally now I can state the theorem about fusion rules. Okay, so the statement is this. So I have now this S matrix SP, so a W algebra associated with a subregular nilpotent at this level here will now be given by, I have SP, which is the usual affine fusion S matrix. So now what I have to do is, so the coefficients of this matrix are given by these sums over the Weil group, and every entry here is given by this exponential. So typically, oh, well, I'm sort of ignoring some detail, but these lie in some cyclotomic field, because this is an integer, or at worst sort of a rational number, maybe divided by they're close to being an integer. So these are close to being kth roots of unity. So they lie in some cyclotomic field. And now, in any cyclotomic field, if I have some number a which is co-prime to the order, then I can just raise a generator to the power of a, and that defines a Galois automorphism of the cyclotomic field. So I apply that automorphism to this S matrix, and I get some new S matrix. And similarly, I have to apply the automorphism of order P to this funny new sigma S matrix, And now I tensor the two together, which is a Kronecker product, right? So in particular, I'm saying that I have a basis, or rather that the set of irreducible modules of this vertex algebra is parametrized by pairs of irreducible modules, one of this algebra, or in P subregular times P regular. And the H matrix is just given by the product of the coefficients of the S matrices, sigma and S. So in particular, if I let f of v denote the Grothendieck group of the category representations of vertex algebra V, this becomes a ring because of the tensor product between modules. And then I have that this fusion ring of this subregular W algebra is isomorphic to the tensor product of the fusion ring of the WZW model. Tensored with the fusion algebra derived from this strange new sigma S matrix. And the reason that you can derive this corollary directly from the theorem is because the Velinde formula computes all of the structure constants in the fusion algebra directly in terms of the entries. And the structure constants obviously have to be integers, because you tensor two modules together. It's then a direct sum of other irreducible modules, and all the coefficients are integers. So if you apply since everything is compatible with this, with these Galois automorphisms, if you apply the Galois automorphism and then apply the Velinde formula, you have to get the same answer as if you didn't apply it. Okay, so a particular corollary. Sorry? But if it's SLN, then it would be n minus 1. Yeah. So it's AN and Q. Yeah, so it turns out that if G is AN, the only value of Q that satisfies the assumptions that we had to impose is that Q is actually equal to N. Well, in that case, the fusion rules are given by fusion rules of yes, yeah. So, so for every Lie algebra, there's only a very specific set of Qs for which this works. So if Q is AN,
that map was many to one. So for a particular Q, you got a unique nilpotent, but the other way around, so you have many Qs that might give you the same nilpotent.
Mm-hmm.
Depends on the type.
Yeah. I'll state a few of the cases, about 2 minutes. So the simplest case of G equals AN, there's only one value of Q that works, which is Q equals N. And then we have this isomorphism here. It turns out that this the index set for the sigma is just a singleton. So this side is trivial, so this disappears. So the conclusion is that the fusion rules of the subregular W algebra in type AN are exactly the same as the fusion rules of a type AN affine vertex algebra. They're not the same as modular categories, because the conformal weights of the modules are different, but the structure as a tensor category is the same. For other types, it gets more interesting. So I don't want to erase this because... So if anyone's interested in a elementary looking but potentially hard problem, how do you see directly that this thing is independent of x? Oh no, here's one I'm going to erase. Right, so in the AN case, well, we just have that this extra part is trivial. But in the other cases, it can be non-trivial. So for type Dn, Q can be either 2n minus 4 or 2n minus 3. And then this fusion algebra, in these cases, is given as follows. So in this case, it turns out to be the same as the fusion algebra of a Virasoro minimal model. This is if n is such that this doesn't also become a multiple of 3. In the case of 2n minus 3, it's also a Virasoro minimal model. For E6, level 9, so if you use this, then you plug this into this side, and then you get an explicit description of the fusion rules for the W-algebra. For E6 at level 9, it's again trivial. Level 10, it turns out to be some W-algebra of type A2, a regular W-algebra. And in these cases, in some cases we know what it is, some cases we don't. In the cases we don't, it seems to be very interesting. It seems to be some possibly very new class of vertex algebras. Yeah, so I mean, yeah, what more can I say? I guess I'll stop here. Fix the, you mean, so for example in this isomorphism here.
Yeah, so the fusion categories are not the tensor, the representation categories are not the tensor product, but can perhaps, if I take another polymorphic vertex algebra, it also will have the trivial.
Well, no, I don't think so, because the conformal weights, the T matrix is determined by the conformal weights, and then they won't change. So you'll still have a discrepancy between the conformal weights, and they determine the twists in the modular category. So yeah, you can't manipulate it that way.
Is there any way of constructing this vertex algebra directly from, or you just found out that these are the guys that actually give you this?
Right, so here I've been a bit ambiguous here. I've said that here that the fusion algebra determined by this S matrix coincides with the fusion algebra of this vertex algebra. More is true. In fact, I mean, if you choose P so that this side disappears, or in other words, if you choose P equal to H, this side disappears, and then you get that this fusion algebra is equal to fusion algebra of this vertex algebra. So then you ask, well, is there actually an isomorphism between the subregular W algebra and whatever it is that you got here? In other words, right, so is this vertex algebra isomorphic to this one? The answer is yes. You can prove this using asymptotics of the characters. So if you you have this notion of asymptotic growth of the characters of a Virasoro module, or of a, say, a vertex algebra.
That thing is not right. It's a W algebra at critical level.
What?
Aren't you taking minus H?
No. I'm taking P equal to H. Oh. So it's minus H plus.
Not 0, yeah, I'm sorry.
Yeah. You can using modular invariance, you can compute the asymptotic growth of this vertex algebra, and it's less than 1, and it has the same central charge as the Virasoro module. So the only thing it could be is the, well, either the Virasoro algebra or an extension thereof. In these cases, it turns out to be equal. In this case, it turns out actually to be an extension. In some of these cases, it's also equal to a Virasoro minimal model. In some of the other cases, the asymptotic growth is greater than 1, so it's definitely not a Virasoro minimal model. Yeah, but even in those cases, we can compute the fusion rules. We're just not really sure. They just aren't equal to anything that we can identify.
You mentioned variety that using the hypothetic orbit.
Yeah.
And okay, perhaps you could give me the example of this variety for n equals 2, 3 equals 4, but conformal algebra.
No, I couldn't. I think Tomiyuki would be much better to.
But it's a known answer for this algebra. But in principle, I mean, there is nothing that forbids defining it. It's just difficult to do. Okay, thank you.
Any more questions? All right, so let's thank Jethro again.
Thank you very much.
And we made it to third.
The associative variety. Yeah, I wasn't. But if n equals 2, d equals 4, that sounded like so much physics.
Presumably, Tomiyuki and this competition doesn't make any sense. The question.
Yeah.
So the question about the inclusion, I'm a little bit confused. So you mentioned this equation.
Legal porque não é tão caro, mas os lugares que eles dão no papelzinho, só que são melhores. Não sei. Assim, a gente pode descer lá e tu vê quanto é.
And then this theorem is telling you that the irreducible representations of the affine algebra at principal level K are the irreducible representations of that affine algebra that come from that are irreducible highest weight lambdas, or these are lambdas.
You derive this from.
Yeah, I don't understand why that theorem is a theorem. So I would have expected this to be true. I mean, a set of